Hi everyone, it's Wednesday, which means it's time for another Chem Help ASAP live stream. As usual, OG benchmarks, if you can let me know if my audio is okay here, that would be great. So we are hard on exam time. Some of you may already be in exams. You're looking at exams starting either this week or next week. So I thought I would take this opportunity and do applications of thermodynamics in this live stream. So this is going to be, if you're like in AP chemistry, this is going to be your unit 9. If you're in first semester Gen Chem, this is also probably going to be towards the end of your semester. If you're in second semester Gen Chem, this is maybe a review from the stuff from the beginning. But anyway, let's go ahead and I'm not on the right mic, huh? Oh, volume is okay. Oh, that's interesting that it's not picking up that one. Let's try this one. Or maybe mute that one there. So on my end, it says it's picking this up, but it could be picking it up from the webcam. As long as you can hear me, we'll go with that. Okay. So anyway, one thing I did want to just mention is because we're headed into summer, so if you are in an intro level chemistry course, and you're looking at taking AP Chem in the fall, then I am offering a prep course for those students who really want to do well in AP Chem, who are looking not only just to do well in AP Chem, but also to continue their chemistry education. So you might be pre-med, pre-dental, pre-nursing. You might want to go ahead and go for your science degree, all that. All of those kind of students are probably going to really benefit from an AP Chem prep course. So feel free to message me on Facebook. You can also email me as well. Okay, with that being said, let's go ahead and jump into our first problem. Okay, here we go. So, applications of thermodynamics. We're going to do a lot of delta G, delta S, and delta H today. Okay, so this first problem reads, when the body metabolizes glucose, energy is released, and here is just the metabolism of glucose. So this is just the oxidation of glucose. This is a combustion reaction. Now, the nice thing about this problem is they've already balanced it for us, so that's great. Okay, and they give us the enthalpy, or the delta H, for this reaction. It is negative 2,801 kilojoules per mole, and very important to know the temperature. It's 298 K. And the first question they ask is, what is the entropy change? Remember, entropy is S, so what is the delta S for this reaction? Now, we're assuming we're still at 298 K. All right, so let's go ahead and calculate A, and I did give myself extra space this time as well. So, but I think we can fit, at least we can fit A on this page right here. All right, so I'm going to put A here. Right, so we know delta H. How are we going to calculate delta S? Well, the great thing is they have given us a table down here of our entropy values for all of our compounds. So when you're given your values, and this can be true for enthalpy, delta H entropy, delta S and Gibbs free energy, or just the free energy delta G, we're going to use products minus reactants. Okay, so this is the sum of the products minus the sum of the reactants will give us delta S. All right, so this is actually pretty easy because we've already got our balanced chemical equation. Obviously, if you have a chemical equation that's not balanced, balance it first because we're going to need those stoichiometric coefficients. So let's take a look here. So our products, we have 6 carbon dioxide. So I do need that stoichiometric coefficient in front. Now I'm just finding my carbon dioxide. Here it is, 213.6, and that is joules per mole times K. Plus, you know what, I'm going to do brackets, so these are products. I have 6 waters, so again, I need a 6 as a multiplier here. Finding water is 69.9, and that is still joules per mole K. Okay, so that's it for our products, and now we're going to subtract our reactants. Our reactants are glucose. There's only one of these, so that's an easy one. Still joules per mole K. Plus our other reactant is oxygen, and I have 6 of those, so that one is 205 joules per mole K. So the main problem that I see students have with this equation, of course, this equals delta S, are two things. First, they forget that this is a minus, or they'll flip-flop products and reactants. The other thing that students will forget to do is they'll forget to use their stoichiometric multipliers. So just don't forget to make sure your equation is balanced and use those stoichiometric coefficients as your multipliers. Okay, so at this point, now that we have all of our numbers in, we're just plugging and chugging into our calculator. Okay, so if I put this all in my calculator, then I get 258.9 joules per mole K. And that is my value of delta S. So actually pretty easy, just products minus reactants. Make sure there's no questions. Okay, let's go ahead and go on to B. So let's read it first. So what is the free energy change? That, of course, is delta G for this reaction. All right, so we have delta H. We now have delta S. So we're going to calculate delta G. So for this one, we're not going to use products minus reactants because we don't have any of our free energy values for our reaction. What we are going to do is we are going to use the classic delta G equals delta H minus T delta S. All right, so this is where T here is temperature, and of course we have the temperature that is 298. All right, so I'm just going to plug and chug again. They gave us our enthalpy, our delta H. That is negative 2,801 kilojoules per mole. Minus T is our temperature, is 298 Kelvin. And we just calculated our delta S. That is 259 joules per mole K. Okay, so we're coming up on usually the first mistake that students make in this type of calculation. Our units here don't match. Now our Kelvin will cancel, so that's great, that's not a problem. The nice thing is they went ahead and gave us the temperature in Kelvin. But you can see that delta H is given in kilojoules, and delta S we just calculated in joules. How did we know it was joules? That's a good question. So if you look at the table, you'll see this is joules per mole K. Again, this is joules per mole K. So what we need to do is we need to convert this joules into kilojoules. Now it's an easy conversion, but again, students don't pay attention to units and they forget to convert. So don't forget to pay attention to your units and make sure they match. So if you are adding numbers, your units should match exactly. So this is just a simple divide by 1,000. Now that is kilojoules per mole K. So at this point, my units are going to match. And I'm just plugging into my calculator. Sorry, this is standard here because all of these are at standard conditions. And my delta G is negative 2,878, and that is kilojoules per mole. So you could see if you forgot to convert your joules into kilojoules, you would have a completely different number. So just watch those units. Okay, so let's see what the next piece is. So that's delta G. Sketch out the reaction coordinate diagram for the metabolism of glucose. Okay, so this is where we just need to specify that it's exothermic. We'll need to show delta H, and if we want, we can also show our activation energy too. Okay, so our reaction coordinate is going to be energy on the y-axis, and this is increasing as you move up the y-axis. And on the x-axis, this is just our reaction proceeding from left to right. So what we know about this reaction is we know that our enthalpy is negative. That means this is an exothermic reaction. So we need to show that that delta H is negative when we draw our reaction coordinate. So what we're going to do is we're going to start with reactants up here. You go through an activation energy and make sure your products are lower. So here are your reactants, the energy of your reactants. Here is the energy of your products. Let's switch to a different color. So this difference here is your delta H, and notice that it is negative. So this is an exothermic reaction, and it has a negative value for delta H. The other thing that we can show in here that's very common, although I guess the problem didn't specify it, is we can show the activation energy. I'll show that in yellow. So that is the difference between the energy of the reactants and the top of this curve right here. And we usually label that EA. That is our activation energy. Okay, so that is our reaction coordinate for this particular reaction. I think we've got one more part for this one. Okay, yes, so part D. If 15 grams of glucose are metabolized, how many kilojoules of energy are released? Okay, so now we just need to do a calculation. See, I gave myself an extra page, but I'm going to need another one. So let me give myself an extra page here. All right, so we're starting with 15 grams here of glucose. This is part D. So 15 grams of glucose, that's C6H12O6. All right, so always a good move, especially if you're not sure how to do a problem. If you're given grams, convert it to moles. That's just always a good rule of thumb, especially if you're looking at taking an exam and you say, well, I want to get some points for this problem, and you maybe know that you can't get all the points. Convert grams to moles, always a good place to go. Okay, so this converts our grams to moles. Now what we want to do is we want to think about our moles of glucose in terms of moles of reaction. Now this one is actually really easy because if I go back to my balanced chemical equation, you can see that my stoichiometric coefficient in front of glucose is 1. So that means for 1 mole of glucose, I've really got 1 mole of reaction. So when we look at like enthalpy here, kilojoules per mole, this is really your moles of reaction. And we'll have another problem where we won't necessarily have a 1-to-1 ratio. So my next conversion is to go from 1 mole of glucose specifically to 1 mole of my reaction. And that ties into my delta H, which we already know. So for my delta H, that's negative 2,801 kilojoules per 1 mole, again, of my reaction. Now, this is why a lot of times when you see, if you look up in tables, enthalpies for reactions, the very first reactant is always a 1. And then you might see some fractions for the other reactants, but they like to make that first reactant 1 because that means your 1 mole of that reactant is the same as your 1 mole of reaction. But it's not always the case. It's just usually the case. All right, so let me just show here how my units are canceling, because what I'm looking for is I'm looking to calculate how much energy, and that means either joules or kilojoules. In this case, it is going to give me kilojoules. So now I just am putting this in my calculator and letting it give me my answer. So my final answer is 233.2 kilojoules. And I think the problem specified, yes, kilojoules. So that's one thing you want to look at when you're reading problems is oftentimes it will specify if it wants the energy in joules or kilojoules or something else. So just make sure you pay attention to those little details. Otherwise, you're talking about, losing a point or two that you could have gotten easily just by reading carefully. Okay, so that is our first problem. That's our first application of thermodynamics. Let's go on to our second one here. All right, so we have another combustion reaction. This is the combustion of methane. So this is a pretty simple one. Again, they did give us a balanced chemical equation, so that's always very handy. We have been given some bond energies here, and part A says we would need to calculate the enthalpy or the delta H of this reaction. Okay, so we can't use products minus reactants, but we can calculate delta H by using bonds broken minus bonds formed. Okay, so this is for part A. We're going to calculate delta H is equal to the sum of the bonds broken minus the sum of the bonds formed. Okay, so this is just another way to calculate enthalpy. There are really 3 general ways to calculate enthalpy. You can do products minus reactants, bonds broken minus bonds formed, and you can also use Hess's law. I do have a live stream on those. It was a couple of months ago. So if you're interested in figuring out how to calculate delta H 3 different ways, you can go check out that live stream. But for this one, because we have been given bond dissociation energies, we're going to use bonds broken minus bonds formed. Now, that makes this problem a little bit more difficult because we have to figure out what the bonds are first before we know if they're broken or formed, which means we need Lewis structures, which is why they did not ask us that on the glucose problem. They asked us that for the combustion of methane. So let's get Lewis structures written out for this entire reaction. So first we have the Lewis structure for methane, and hopefully these are simple enough that you're not having to struggle to draw these Lewis structures, especially if you're looking at the AP exam coming up. They're going to expect you to be able to crank out these Lewis structures pretty easily because these are pretty simple and you should have seen them in class probably multiple times even. Okay, that's carbon dioxide, and I have 2 waters here. Now, the nice thing about doing these Lewis structures is we're not worried about molecular geometry, so you don't have to worry about the SEPR, we don't have to worry about hybridization. We just want to see what the bonds are because we need to figure out which bonds are broken and which bonds are formed. So I'm going to start with the bonds that are broken, and I'm going to mark them. So if I'm looking at my methane here, I have 4 carbon-hydrogen bonds. I don't preserve any of them in the product. So all 4 of these are broken. And if I look at my oxygen, of course I have 2 oxygen molecules, so don't forget that 2 there. Yes, I am breaking that oxygen-oxygen double bond. So I'm breaking all the bonds in my reactants. So let me just write that down. I'm going to put that up here. So let's go bonds broken. I want to make sure I don't come into my my webcam. So my bonds broken, I have 4 carbon-hydrogen bonds that are broken, and I'm going to have 2 oxygen-oxygen double bonds that are broken. Okay, and that's it for my bonds that are broken. Let's take a look at my bonds that are formed. I'll use a different color here. Let's use yellow. So I have 2 carbon-oxygen bonds here. Yep, those are not preserved from the reactant, so those are new bonds that are formed. And also I've got my oxygen-hydrogen bonds right here. These are also formed. Don't forget you have a 2 here, so that is a multiplier. So if I look at my bonds formed, I have 1, 2 carbon double bonded to oxygen formed, and I have 1, 2 times 2, I have 4 hydrogen oxygen bonds formed. Okay, so you can see that my table is going to give me all of this data that I need. I just need to now plug it into my bonds broken minus bonds formed, and I can actually get this calculation done. I am going to try to put this on this page. Since we have all our data on this page, I'm going to put it in green so it stands out a little bit. Okay. So our delta H is the sum of our bonds broken. Again, I've listed our bonds broken here. That is 4 times our carbon-hydrogen bond, which is 415 kilojoules per mole, plus I have 2 oxygen-oxygen bonds broken. That's 495 kilojoules per mole. Okay, so that's my bonds broken minus my bonds formed. I have 2 carbon-oxygen double bond. Here we go, 799 kilojoules per mole. And I have 4 hydrogen-oxygen or oxygen-hydrogen bonds here, 463 kilojoules per mole. Again, these multipliers are obviously really important. And again, the most common thing I see is students forgetting to take these stoichiometric coefficients into account. All right, so at this point, again, I'm just plugging into my calculator, and that is going to give me my delta H. And for this reaction, that is negative 800 kilojoules per mole. Again, make sure you pay attention to your units. I get my units from my table right here, kilojoules per mole. Okay, all right, so that is part A. Let's take a look at part B. So if you need 1,500 kilojoules of heat, how many grams of methane should be combusted? So this is just like the previous problem where we combusted like 15 grams, except it's reversed. So now we know how much we want to get out, and we want to figure out how many grams in this case of methane, should be burned. Okay, so let's go ahead and do that. Just like before, this is just a dimensional analysis problem. That's all we're doing, is just we're doing dimensional analysis. It feels like it should be more than that, but it's not. I'm just going to make sure that my units canceled. Okay, so we wanted to get out 1,500 kilojoules of energy. Well, if we go back and we take a look at this, we have just calculated that per 1 mole of reaction, we're going to get 800 kilojoules out. So that is my next conversion factor here. So for 1 mole of reaction, I am going to get out 800 kilojoules of energy. Now notice my units here are going to cancel. That's exactly what I want. All right, so now I need to convert out of my 1 mole of reaction to whatever moles that I'm talking about in my problem. And this one asked me for methane, so looking at my balanced chemical equation, okay, so it's a 1-to-1, so that makes it nice and easy. So this goes to 1 mole of methane. And then finally I need grams, so that's just a simple mole to gram conversion using the molar mass. So one thing that I think students underestimate is the power of dimensional analysis. Here we are using it for what could be considered a complex reaction, but all I'm doing is I'm making sure that my units cancel. I'm just doing dimensional analysis. So let's go ahead and show that cancellation. This is going to give me grams of methane. That's exactly what my problem asked for. So that gives me 30 grams of methane. All right, so that's how much methane I need to get 1,500 kilojoules of energy out. Let's take a look at the next problem. Okay, so sorry, I'm on part C. We just did part B. So the free energy change, that's G of this reaction, is negative 801 kilojoules per mole at 298, and calculate the entropy for this reaction. All right, so we have our delta H. We now have our delta G. We want our delta S, and we have our temperature, so we're going to use delta G equals delta H minus T delta S. That one's actually pretty simple. Okay, so delta G is equal to delta H minus T delta S. We were given our Gibbs free energy, that was negative 801 kilojoules per mole. We calculated our delta H, that was 800 kilojoules per mole. Our temperature is 298 Kelvin, and we are calculating our delta S. So this is just really a plug and chug situation. So I can calculate my delta S, and that is 0.00336 kilojoules per mole K. Okay, remember this K here, this Kelvin came from that temperature there. So just again, watch your units. Now, usually when we calculate delta S, we don't calculate it in kilojoules. You can see why, it tends to be small. Now, the problem didn't specify this, but usually, again, you report delta S in joules per mole K. But that's where, again, reading the problem carefully can make all the difference, because sometimes they will specify what units they want it in, and sometimes they won't. Okay, so that is delta S. And our last part here is explain the sign of delta S as well as the magnitude and the value. Okay, so we got a very, very small value for delta S. I mean, this is almost 0. So what is going on with entropy in this reaction right here? Well, one thing I notice is we have the same number of moles on both sides. So we have 1 plus 2. We have 3 moles on the reactant side. We've got 3 moles on the product side. So our number of moles is not increasing or decreasing. That can definitely change entropy. Also, when I look at the molecules we have here, all 4 of these molecules are pretty small. So we're not going from, say, Again, glucose, which is a very large molecule, and breaking that up into a lot of small molecules, that creates a lot more disorder. That's very favorable entropy wise. This one, we're going from small molecules to small molecules. The only thing that I would say is in terms of bond rotation, methane has a lot of freedom in that, so maybe that is why our entropy is just barely slightly positive. But I think your main 2 points here are your moles are equal on both sides, and you're going from small molecules to small molecules, so there's not really a big change in the size of your molecules as well, and that's why your delta S is not only very small, but just barely positive. Okay, all right, so that is the second problem. Now let's go ahead and talk about our last problem here. So this is problem number 3. Okay, so given the following reaction and information, all right, so again, we're given a balanced chemical equation. We've got 2 tables going on here, so we've got a lot of calculations, I think, that are coming. All right, so we need to calculate the delta S. We need to then calculate delta H. We need to figure out if this is favored thermodynamically, and then we need to go with how much energy is released, calculate the energy change, and again sketch the reaction coordinate for this reaction. So we've got a lot of work to do. So let's go ahead and start with A. So we need to calculate delta S for this reaction. So we're given the reaction, so I am immediately going here because this is our entropy for all of our compounds. This is definitely going to be a products minus reactants type of deal. Okay, so let's go ahead and get that in. I'll switch back to blue. So our delta S is going to be the sum of our products minus the sum of our reactants. Again, make sure you're working with a balanced chemical equation because you need these stoichiometric coefficients right here. And we're also going to use these numbers right here. Now, I have these written down, and ideally, if you're working on this at a test, you're not having to switch back and forth between pages, although sometimes you are given a data table at the end of a test that you might have to reference. So that's a little bit of practice with that. Okay, so my products, this is joules per mole K. Plus 3 times 189 joules per mole K. Okay, so you might want to check where these numbers are coming from. So my products, this is 4 times my nitrogen, 3 times my water. Again, I'm getting these from right here. I'm going to do the same thing with my reactants. I'm getting them from right here. Okay, minus my reactants, 193 joules per mole K. Plus 3 times 220 joules per mole K. Now the nice thing is when you're reading a table like this is your units are always going to be consistent. So that is something always to look for, is consistent units. Okay, so our delta S, I am just plugging and chugging into my calculator. This is 289 joules per mole K. All right, so I believe the next part they wanted to calculate enthalpy. Yeah. Okay, so now they want delta H for this reaction. Now we can't use our delta G equals delta H minus T delta S because we don't have delta G yet. So we're going to have to calculate delta H another way. We're not going to use this table because that is for entropy. We're going to, again, we've got bond energies here, so we're going to do bonds broken minus bonds formed. Okay, so for part B, our delta H is coming from the sum of our bonds broken minus the sum of our bonds formed. So this is all about reading your problem and seeing what information you have at hand and using that to, again, especially for delta H, because you have multiple ways to calculate enthalpy. All right, we're going to have to get Lewis structures in here. Okay, so here is our reaction. Again, it is pretty easy. We've just got ammonia and dinitrogen oxide going to nitrogen and water. So I'm just going to draw these in. Again, just because I'm looking at bonds broken minus bonds formed, I don't have to worry about getting the right shape in. Nitrogen. Let me get my lone pairs in here. I guess really you don't have to have lone pairs, but I just can't let those go. 4 nitrogen molecules. And then we've got 3 waters. Okay, giving everything kind of linear just helps with space here. Okay, so let's first figure out which bonds are broken here. So if I'm looking at my ammonia, you can see on my product side I don't have any NH bonds. So all 3 of these are going to be broken, but don't forget this multiplier of 2. Nitrogen double bonded to oxygen, yeah, I'm not preserving those either. So these also get broken, and there are 3 there. So I'm going bonds broken. I'm going to make my list here. I have 3 times 2, I have 6 nitrogen hydrogen bonds that are broken. I have 3 times 2, okay, I have 6 nitrogen double bonded to oxygen bonds broken as well. So let's take a look at our bonds formed. So definitely our nitrogen bond is formed, and our hydrogen oxygen bonds are also formed. So here we have, let's make a list of our bonds that are formed, and we have 4 nitrogen triple bonds, and no, sorry, that's not 3, that's 3 times 2, that is 6. I almost forgot my multiplier. That's 6 hydrogen oxygen bonds formed. So now we're just plugging into bonds broken minus bonds formed, and of course we're going to use these energies here. Now one thing I do want to point out is be careful. So like here's a nitrogen double bond as opposed to a nitrogen triple bond. So when we're talking about our nitrogen triple bond here, just be careful that you're plugging in the triple bond energy and not the double bond energy. Again, that's a really easy and it's a common mistake to make, is just plugging in the wrong numbers there. Okay, so our delta H is going to equal 6 times nitrogen hydrogen, this is kilojoules per mole, plus 6 times our nitrogen double bonded to oxygen. Okay, so that's our bonds broken minus our bonds formed. We have 4 nitrogen bonds. Again, those are the triple bonds. And we have 6 oxygen hydrogen bonds right there. And now that we've got everything in, again, it's pretty simple to just pop this into your calculator. Sorry, I keep forgetting my standard state there. And we get negative 434. And of course, this is kilojoules per mole. Again, I get my units from my table right here. So just, again, watch those units. Because for our next one, C, is this reaction favored thermodynamically? Well, to know if it's favored or not favored, we really need to know the sign of delta G. So we might as well calculate our delta G. Let me get myself another page. Great. Okay, so this is part C. So remember, delta G is equal to delta H minus T delta S. If we're calculating delta G, we just did delta H, so that's kilojoules per mole, minus T. What was our temperature? So when we're not given a specific temperature, then you want to assume that you're at 25 degrees C, which is 298 Kelvin. So 298 Kelvin. And then we want to plug in our delta S, which we also calculated at 289 joules per mole K. All right, once again, we've got to be careful because we have a mismatch here in units. So just always, always be aware of your units. I know you guys hate writing your units down, but if you don't write it down, I promise you're not going to catch this unit mismatch. And that makes a huge difference because I just divided that by 1,000. Okay, so now we can plug this in and we get a value of delta G of negative 520 kilojoules per mole. Now we're not so interested in the 520. What we're really interested in is the fact that this is negative. So a negative delta G equals a favored reaction. Okay, so yes, this reaction is favored thermodynamically because our delta G is negative. All right, let's go to our next part here. All right, so D, 25 grams of ammonia reacts with 25 grams of dinitrogen monoxide. Will energy be released or absorbed? And then calculate the energy change. Well, this first part we can go really easy. Will energy be released or absorbed? We calculated the delta H for this, and we got it right here. This is a negative delta H. This means this is an exothermic reaction. So yes, even if you reacted a tiny amount, still you're going to have energy released because this is an exothermic reaction. So energy is definitely going to be released, but now we need to calculate the energy change. Now what makes this difficult is we are given information on both of our reactants. That means we need to figure out which one is the limiting reactant, and then once we know which one is the limiting reactant, then we can figure out how much energy is released. So in this problem here, they have thrown in a limiting reactant problem in the midst of a thermodynamic problem. All right, so first we'll say energy is released. And now let's actually calculate what that energy is. Okay, so just like I said before, if you're unsure what you should do and you're given grams, just convert to moles. Always a good bet, right? We just always work in moles. We don't work in grams because we need to keep track of our number of atoms. Okay, so this gives us 1.468 moles of ammonia. And let's do the same for our dinitrogen monoxide. Just convert it to moles. That molar mass is 44.01320. This gives me 0.5680 moles of dinitrogen monoxide. All right, so just looking at this, I'm going to guess that probably my dinitrogen monoxide is my limiting reactant, but we need to actually test it and find out, because this is not a 1-to-1 stoichiometric ratio. This is a 2-to-3 stoichiometric ratio, so you want to be careful with that. You can make your best guess, and that's fine, but just double check that with a mathematical test. Okay, so if I'm going to use, all of my moles of dinitrogen monoxide, how many moles of ammonia do I need? So I'm just doing a mole to mole ratio here from dinitrogen monoxide to ammonia. And this tells me that I need 0.3787 moles of ammonia. That's how much is needed to react all of my dinitrogen monoxide. And you can see I have lots more than that. So I've got almost, I've got multiple times what that is. So yes, my dinitrogen monoxide is my limiting reactant. Make sure you mark it really clear. So now I'm going to use that moles, and I'm going to figure out how many kilojoules of energy is released. So starting with my moles of my limiting reactant, 680 moles of dinitrogen monoxide. So this is again very similar to the same calculation that we did for the first two problems as well. So we've got 1 mole of our reaction is 3 moles of dinitrogen monoxide. And how do I get that? Ooh, one more. So that is from this stoichiometric coefficient here of 3. So in our other two problems, the molecule that we were concerned about, either the glucose or the methane, had a stoichiometric coefficient of 1, so it was just a 1-to-1 ratio. It was really easy. If you forgot it, it wasn't a big deal. But in this one, we've got a stoichiometric coefficient of 3 there. So that is where making sure you convert from just moles to moles of reaction makes a big difference in your answer. And then we have our delta H value for this, and that is negative 434 kilojoules again per mole of reaction. And again, you can see units are canceling. It's all about your dimensional analysis. Okay, so if I put this in my calculator, I get 82.2 kilojoules. So that is how much energy is released if you react 25 grams of ammonia and 25 grams of dinitrogen monoxide. You're going to have a good bit of ammonia left over. Okay, so we've got one more part of this. This is E, sketch the reaction. Okay, so sketch the reaction coordinate for this reaction again. So we'll go ahead and label these as well. So our reaction coordinate has energy on the y-axis. It increases going this way, and our reaction proceeds going from left to right. This is an exothermic reaction because our delta H is negative, so it's going to look the same as our previous. Let's go ahead and show delta H. So that is the difference here between our reactants and our products. That is delta H. This is an exothermic reaction. And we can also put in, mark this out, our activation energy. And that is just our hump right there. So this is our reaction coordinate for an exothermic reaction, which this is. Okay, so I think that is it for this last one. Yeah, it was just to sketch the reaction coordinate. So if you have requests for other live stream topics, let me know. Again, I know you guys are coming up into exams. Some of you maybe are already taking your exams before the next live stream, but if you need to see some problems work as you're studying, you can always let me know. You can let me know. You can message me on Facebook. You can leave a comment in this live stream even after it's over, and you can also email me and let me know what you would like to see. But I hope that studying for exams is going well, and I hope that this helped you guys. So I'll talk to you later. Bye.